Hello, my name is Mrs Kershaw and I am one of the Science Directors with Outward Grange Academies Trust. Our topic today is nanoscience, and this is for students who are studying the chemistry only pathway. So our challenge today is to be to calculate the surface area to volume ratio, and our aspire is to be able to explain the benefits of using nanomaterials and give examples of their uses. To start with then, a bit of maths. During our lesson today we are going to need to be able to use standard form, so I'd like you to start by converting these ordinary numbers to standard form. 1 minute, off you go. How did you get on then? Things that we need to remember then is that the number was less than 1, so the power of 10 is going to be negative. Secondly, the number to the left of the decimal point must always be between 1 and 9. Can you now then convert these standard form numbers to their ordinary numbers? And here are the answers. This time then a mixture of ordinary numbers and standard form. Can you fill in the missing blanks? and self-assess. That's great then. So we've looked at standard form, and here are some common scientific prefixes. And again, these are things that the exam board expect you to be familiar with. So today's lesson, we're going to look at nanoscience. So this is particles that are round about 10 to the minus 9 meters. And just to put that into some context, an atom is typically 1 times 10 to the minus 10 meters. So nanoparticles are bigger than atoms and will typically consist of 1 to 200 atoms. Something students often forget then, atoms are smaller than nanomaterials. Nanomaterials are made of atoms, so therefore by definition must be bigger than atoms.
I'm sure you've calculated areas in maths. So if we look at the first square, then each side is 2 centimetres. So the area equals 2 times 2, which is 4 centimetres squared. What you need to remember is if we've got a three-dimensional object, then we need to calculate the area of every side and then add them all together. So if again we had 2 centimetres by 2 centimetres, and that it's a perfect cube, so this way is 2 centimetres as well, then the area of one side equals 2 times 2, just like it did on the square above, which is 4 centimetres squared. But we need to remember that this time we have 1, 2, 3, 4, 5, 6 sides. So 6 sides, and this equals 4 times 6, which will be 24 centimetres squared. So that would be how we worked out the surface area for the cube. We work out the area of one side and then we add that together for each of the 6 sides.
Right, so first of all, I'd like you to now calculate the surface area of the cube. And to do this, you're going to need to calculate the area of one surface, and then the cube has 6 surfaces, so you'll need to times that by 6. So how did we get on then? The area of one side is 6 times 6, which is 36 centimetres square. The cube has 6 sides, so the total surface area must be 216 centimetres squared. Right, for this one then, I'd like you to calculate the surface area of the large cube, then calculate the surface area of the small cube, Then look at the large cube, and if we divided it into 8 of the small cubes, what would its total surface area be? And can you express the answers to question 1, that's the surface area of the large cube, to question 3, which is the surface area of the 8 small cubes? I realise this is quite a bit, so I'm going to give you 5 minutes to do it. let's see how you got on then. So the area of the large cube is 16 centimeters squared for one side. So for all 6 sides, it's 6 times 16, which is 96 centimeters squared. The total surface area of the small cube then is 4 centimeters squared for one side, times that by 6, and we get 24 centimeters squared. If the large cube then is divided into 8 of the smaller cubes, each of the small cubes has a surface area of 24 centimeters squared, but there are 8 of them, so that makes 192 centimeters squared. So if we express that as a ratio, the answer from question 1 was 96 and the answer to question 3 was 192. So it's 96 to 192. But as you know, we need to simplify that if it's a ratio. So it's 1 to 2. I'd now like you to calculate the volume of the large cube, the volume of the small cube, and again if we divided it into 8, what the total volume of the 8 small cubes would be, and again can you calculate that as a ratio? Okay, so the total volume of the large cube is 4 by 4 by 4, which is 64 centimetres cubed. The total volume of the small cube is 8 centimetres cubed. And if we divided the large cube into 8 of the smaller cubes, then we've got 8 times 8, which is 64. So the volume, if we express 1 and 3 as a ratio, is 1 to 1. The volume would be the same. So surface area to volume ratios. If we look at the small cube, we've already calculated that its surface area is 24 centimetres cubed. Its volume is 8 centimetres cubed, so its surface area to volume ratio would be 24 to 8, or simplified, that would be 3 to 1. Comparing that to the large cube then, its surface area is 96 centimetres squared, its volume is 64 centimetres cubed, and therefore its surface area to volume ratio 96 to 64, which we can simplify as 3 to 2. This means that the smaller cube has a much higher surface area compared to its volume than the large cube, i.e. it has 3 times as much as opposed to. For each of the two cubes shown, I would now like you to calculate the surface area to volume ratio for each cube. For each one you'll need to calculate the total surface area, and for each one you'll need to calculate the volume. Once you've done that, I'd like to tell me if there's a pattern. 4 minutes, off you go. Okay, for the small cube on the left then, that you can see that the surface area is 6 centimetres squared and the volume is 1 centimetre cubed. That gives us a surface area to volume ratio of 6 to 1. For the large cube then, the surface area is 600 centimetres squared and the volume is 1000 centimetres cubed, and its surface area to volume ratio is 6 to 10. You can see I further simplified that underneath and I've got one of the sides as 1. In maths I realise that you do ratios to whole numbers, but in science we always have one side as a 1. However, if I look at the 6 to 1 and the 6 to 10, you can see that by increasing the length of one side by a factor of 10, we have decreased the surface area to volume ratio by a factor of 10. Okay, nanoparticles then. They have a high surface area to volume ratio, and that's really good because it means you can use less of the material and achieve the same effect, so it's more cost effective. Here we have a question where the exam board have asked you to calculate the surface area to volume ratio for the nanocrystal. Okay, so the surface area is 2,400 nanometers squared and the volume is 8,000 nanometers cubed. So the ratio is 0.3 to 1. Noticing again what I said before about the fact that in science, one of our sides of our ratio is always 1, so we will have decimals. It's not always whole numbers. Silver nanoparticles then are sometimes used in socks to prevent foot odour. Suggest why it's cheaper to use nanoparticles rather than the coarse particles. And remembering, suggest is just coming up with a sensible idea using a bit of common sense and some science. 2 minutes for you to think about that. Right, so what they wanted you to say were that nanoparticles have a larger surface area, so that means that you can use less of them for the same effect. So what other uses do we have of nanomaterials? Well, we can use them in sun cream. So zinc oxide and titanium oxide are used in sun cream because they absorb the harmful UV rays from the sun. We can use them in plasters and bandages, and we put nanocrystals of silver in there because it's toxic to bacteria. As you've seen in the previous question, we could also use it in socks. Both of these would kill bacteria and prevent infection. And we can also have fabrics with nano coatings so that they will repel liquid and become stain resistant. Here are some other examples.
Exciting scientific breakthroughs such as nanotechnology are promising to revolutionize cancer therapy. Scientists here at the Siteman Center of Cancer Nanotechnology Excellence are making great progress, discovering new ways to improve the diagnosis and treatment of cancer. At the Siteman Cancer Center, researchers are actively pursuing many ways in which nanotechnology can greatly improve cancer diagnosis and cancer treatment. Diagnosing and treating cancer can be a challenge because tumors can hide anywhere in the body, and anti-cancer treatments like chemotherapy and radiation affect normal tissues, not just cancer cells, causing side effects. Nanotechnology is a revolutionary new approach to cancer that's showing great promise. What is nanotechnology and how does it work? Nanoparticles are incredibly tiny, so small that 100,000 of them would fit on a single human hair. Nanoparticles can be administered to patients intravenously. They easily float through the bloodstream, seeking out cancer cells wherever they may be hiding. Some nanotechnology is designed to seek out cancer cells and attach to them, using specialized receptors which bind to the tumor selectively. Once bound to the tumor, the nanoparticles send out signals that tell doctors where it's located. This can help accurately visualize tumors that would not show up on conventional medical scans. Other nanotechnology is designed not only to find the cancer cells, but to kill them selectively using specific receptors that attach only to the tumor without injuring nearby normal tissues. With time, the nanoparticles are completely eliminated from the body. These are just two applications of nanotechnology for treating cancer. Siteman Cancer Center researchers are investigating many other nanotechnology applications against cancer. In the not-too-distant future, nanotechnology will revolutionize the approach to cancer and greatly improve the quality of life for people with cancer and their families.
So what future uses of nanoparticles? Well, medicine would be somewhere that we might have some really good uses for it. So we could put nano coatings on hip and joint replacements, and that would help to prevent rejection. And we can have nanoelectronic implants in the retinas of blind people, which would communicate with the cells and possibly even make it possible for them to see again. We can use nanocapsules of drugs that will target cancer cells only, rather than having chemotherapy drugs that attack all cells. This is much more beneficial and would lead to a lot less side effects for people having those kind of treatments. We can use nanoscaffolds to be able to support the growth of new tissue, skin and body tissues, and nanosensors inside of clothes or even inside our bodies that will be able to run health checks and deliver medicines when it's appropriate. So I'd like you now, considering what we've learned over the last few slides, to give 2 current uses of nanomaterials and 3 possible future uses. And why is the possibility of using nanomaterials in the treatment of cancer so beneficial? 3 minutes. Okay, so uses, we could use them in we currently use them in sunscreen, plasters, socks, fabrics and nanotubes. Future uses, you could have had nano coatings, electronic implants, capsules for the delivery of drugs, scaffolds, sensors. And why would it be beneficial for the use in cancer? Because you need much smaller doses, leading to far fewer side effects. Right, that ends the lesson today. On the following slides you will find some more notes if you'd like to pause the video and make some further notes in your books.